All right, you can flip back one day in your notes and see we explored what the derivative of sine of x over cosine of x was, and we did it using the quotient rule. And what was the result then, if you look back? What did we get? Okay, we got secant squared x. And so that is the resulting proof, actually, for the derivative of tangent. So we can summarize that. We can say, well, then the derivative of tangent, based on the proof of the quotient rule from sine and cosine, worked out to be secant squared of x. That is the derivative of tangent. And we did that with an exploration. In a similar way, you could explore the quotient rule of cosine over sine, and you could figure out what the derivative of cotangent is. And doing the the quotient rule with cosine over sine, you're going to find that the derivative is negative cosecant x. That is one of your homework problems, is to prove that true in the same way that we proved sine over cosine resulted in secant squared. So those are the next two derivatives that you'll need to commit to memory. You've got sine and cosine hopefully committed to memory, and now you've got tangent and cotangent. One thing that helps me remember the negative signs. Any function, trig function, that starts with the prefix co, so cosine, cotangent, or even cosecant, all have negative derivatives. Okay, so it always works, and so if you're ever confused which one is and isn't negative, it's anything that had a co in it. And so, all right, now we should be able, if that's the case, using quotient rule to prove, and you should be really glad that you get to use quotient rule to prove it and not Newton. You only need Newton to prove sine and cosine. Once you've proved sine and cosine, then you can just use quotient rule to prove the other ones, and it makes it a lot easier. So our first example today is going to be, well, then what's the derivative of secant and cosecant? And so we are going to prove the derivative of the secant function, and we're going to use the quotient rule to do it. I think we can fit this all in. All right, so prove that derivative using the quotient rule. Okay, in order to do that, the quotient rule requires a fraction. It requires a numerator and a denominator. So we'll take d dx of the secant, and we'll change secant into its identity form. And the identity form for secant is 1 over what? 1 over cosine. And we're going to apply the quotient rule to that. Okay, so d dx. It's Leibniz's notation, but it doesn't mean we have to necessarily use Leibniz rule anymore. We can use other rules, and so we're going to use the quotient rule to prove this. And so we're going to take b times a prime, and we're going to subtract from that a times b prime all over b squared, and we'll see what we end up with. All right, so b is cosine of x, and a prime is 0. And then a is 1, and b prime is the derivative of cosine, which we learned yesterday and proved to be negative sine, all over cosine x, that quantity squared. All right, so as you look at that numerator, do some mental math of cleaning it up. Look at what the 0 does and look at what the 1 does. And what do we end up with in our numerator? Just sine x. That's it. The 0's gone, the 2 negatives make a positive, and we're left with sine x over cosine x squared. Now we want to simplify that a little bit because that can be written differently. In fact, it might be helpful to me to just have the coefficient of 1 in front of that. Because cosine is squared, I could rewrite this as 1 over cosine and sine over cosine. That's not common denominator, that's just separating a square. A square is something multiplied by itself, so the denominator could look like that, and the numerator could be 1 and cosine. Those are still the same thing using multiplication. And then this comes down to what those are in their identities. All right, so what's 1 over cosine? Secant. And what is sine over cosine? Tangent. And that's the end of the proof. And so we have just proved that the derivative of secant is secant itself times tangent. That is the proof of the derivative of secant. And so again, as part of your homework, you'll be proving the other. So in your homework, you're going to prove what the derivative of cosecant is. Now there's some parallelism to what the answers turn out to be. You can kind of, well, if the derivative of sine was cosine and the derivative of cosine was negative sine, we can kind of see some parallelisms. Here we see that it's a cosecant, and so the answer should be negative. And then based on what it turned out to be for secant, can you take your best guess at what cosecant might turn out to be? If secant turned out to be secant tangent, what do you think cosecant's derivative would be? Cosecant, cotangent, and you're exactly right. Okay, that's the parallelism to it. So what I want to do with you now, that you're going to prove that using the quotient rule. But what I want to do right now is just kind of summarize everything. I want to look at the 6 trig functions and the 6 trig derivatives. We started this chart yesterday, but now we're going to complete it. So we've got everything together, and then we're going to practice with them. So the 6 trig functions: sine x, cos x, tan x, cotangent x, secant x, cosecant x. Those are the 6. And so if you see them side by side, you might start to notice and help you memorize the patterns a little bit better. So we know that sine's derivative is cosine. We know that cosine's derivative is negative sine. So there's the first pairing where the cosine has a negative derivative. I've proven to you twice now that the derivative of tangent is secant squared. And then you will prove that cotangent has a negative derivative, and it's negative cosecant squared. So you'll prove that, and that's the second pairing of derivatives. And then finally, I've proved to you that secant's derivative is secant tangent itself, secant itself multiplied by tangent, and then you are assuming, correctly, that the derivative of cosecant is negative cosecant cotangent, and those proofs are still to come as part of your homework. So what we're going to do is just practice a couple maybe product rules, quotient rules, different derivatives using the new things that you know about trig. So those are the 6. The first thing we want to try and do is to find a tangent line to y equals secant x. And let's do it at the unit x equals pi fourths. So I guess, Jeremiah, you might need a little unit circle for this. Okay, you might for these though, depending. You could either, it depends on how you originally memorized the values of sine and cosine. Did you do it around your unit circle like on my clock? Or did you do it in the wave, memorize it from the shape of the wave? I don't know how you did it, but okay. All right. So, like we've done before, to find any tangent line, you need 2 things. You need to know what the point and what the tangent slope is. So, our point here is going to be pi fourths for x, and then the secant value of pi fourths. So in order to know the secant value of pi fourths, you're going to have to know the cosine value of pi fourths from your unit circle. So who's got it? Okay. That's the cosine value. What's the secant value? 2 over rad 2. You do not need to rationalize. You are welcome to just leave it that way. If you did rationalize it, it would be rad 2. Now we want our tangent slope. And so our tangent slope will be y prime. We've just proven what y prime is, that y prime is secant x tangent x. And so the value of y prime here would be secant pi fourths times tangent of pi fourths. And we know what the secant of pi fourths is from our first problem. So this will be 2 over rad 2 for the secant. And what about the tangent of pi fourths? That's 1. So now you can write your tangent line. Doesn't take a whole lot of effort. And so the tangent line would now be y minus the y value of 2 over rad 2, the slope value of 2 over rad 2, and x minus pi fourths. And that's going to be your tangent line. Okay, any questions about that one? Okay, let's try another one. Let's do a normal line this time. So let's write a normal line to the equation y equals tangent of x over x. So that's the function. And we're going to do it at something not on the unit circle, at x equals 2. Because this is not on the unit circle, things are not going to work out nicely, and that's okay. We don't need to be afraid of it. But we also aren't going to round anything inappropriately, so we're just going to watch out for that. So our point here is just going to be 2 comma tan 2 over 2, or you could also write that as 2 comma half tan 2. Now we don't know what the tangent of 2 is. Tangent of 2 is going to be a fairly large number, but I don't need the decimal value. I'm just going to leave it in its exact form, a tangent of 2. So you're just be comfortable leaving some of these things in numbers that aren't exact necessarily. Okay, our slope. We need to find y prime. This will find us the tangent slope. And we'll do this with what rule? Yep, we're going to need the quotient rule here. So my quotient rule is going to start me out with x times the derivative of tangent, which is secant squared, minus tangent to x times 1. All over x quantity squared. At the y value, or at the x value of 2, this will be 2 secant squared of 2 minus the tangent of 2 all over 4. Again, it's okay to be comfortable leaving these in a form that we can't evaluate without using decimals. It's fine to leave it that way. We're ready to write our normal line. Just remember that you're doing a normal and you're not doing a tangent line. So your normal line would be y minus the y value, that was tangent 2 over 2. What's the normal slope going to look like? How would I write that? Flipped and negative, right. So what's the easiest way to write that? Okay, flip it. 2 secant squared of 2 minus tangent of 2, and then make a negative. Okay, so it'll be negative 4 in the numerator. You don't have to do it, it's not super complex. And then times x minus 2. And that's our normal line. We don't have to distribute it, we don't have to clean it up unless specifically told, please round to the nearest, third decimal or whatever, then you could. All right, any questions on that? Okay. Well, you had a lot less questions on the homework than I anticipated, and so I think you guys are just ready to get started. You can spend the rest of the time having a work day. Tomorrow, we will be starting some physics, and we're going to be talking about how derivatives relate to velocity and acceleration, something called jerk, if you've talked about that in your physics classes, and speed. Okay. All right, so you do have the rest of the time. It's a nice, you should not go home with hardly any homework in math class tonight, I don't think. Okay. What's this already? Okay. I'm just going to give you a head start on some physics stuff that we'll need for tomorrow. I want to talk about velocity, the difference between speed and velocity. If you're in physics already, or if you've in AP Physics, you know that velocity comes from the first derivative, but we just need to distinguish the difference between the two. Okay, to find the velocity, it's going to be f prime of x. It's the first derivative. And that will give you speed with direction. If you know about vectors, okay, a velocity vector. So if it's positive, then the direction is either up or right, depending, but it's basically in the first quadrant if it's positive. If it's negative, then we're talking down or left. The difference between velocity and speed is that speed is the absolute value of the first derivative, and that will give you speed without direction. In our everyday lives, that's what we use most often. We'll say, I was going on the freeway at 72 miles an hour. That doesn't tell you what direction I was going on the freeway. Okay, and I also don't say I drove to school with an average speed of 37 and I drove home with an average speed of negative 37. Even though that's true, because I went everything backwards, and so my vector should say everything's backwards as I'm going back home. So in our language of every day, we don't talk about that. So when you don't include direction, then that is speed, and it's always simply the absolute value of velocity. All right, that's it. That's just a little snippet of what I want to show you for tomorrow. Okay, now I promise I won't interrupt you again.